quantum systems, instead of being degenerate, these two will be in a superposition. And that will be the basis of the flux qubits. If you can actually build a qubit with this configuration, the only problem is that you need the inductance of the loop to be very large, contrary to what has been said in the morning for other applications. For building RF squid flux qubit, you need this inductance to be of the same order of this junction. So this beta parameter should be near 1. And that will result in a potential energy which is a double well potential. And double well potential has two minima that correspond to current clockwise and current counterclockwise. So the eigenstates are superpositions of those. But you need this inductance to be big. So that means the loop needs to be large, and that means it will be sensitive to flux noise. Nobody's using this qubit except for this company called Decay that they sell quantum annealers. So their qubits are not very good. That's the message. Now, in order to resolve this problem, you can replace this big inductance by a couple of junctions, two bigger junctions. That's what I'm drawing here. So this loop that I was showing before, a junction in an inductor, can be replaced by these two bigger junctions. And this loop now is very small. This is only a few micrometers inside. And this is called the persistent current qubit. It was pioneered in the late 90s by the Delft group and the MIT group together. Now this circuit is very interesting. You can write down the Hamiltonian. I just put it here for you to identify how such a circuit looks like when you treat it analytically. So this is the potential energy. We have the cosine of one junction, two junctions, and then the third junction. We're using the flux quantization, or in fact here we call it more the phase quantization, because this is so thin that flux is not really quantized, but phase is. So we have 2 degrees of freedom, phi 1 and phi 2. But if you minimize your energy classically, you find that when the flux is near half a flux quantum, this point that I was telling before, where these two currents are degenerate, then the potential energy is the double well potential. And these are energy levels, so this is already solving this Hamiltonian. And this is the wave function of the lowest 2 states. So you see a minimum of this double well potential represents a classical solution. So it is a finite phase. And the 2 solutions have the same phase but opposite sign. And having a phase across a junction means there is current. So each of these 2 solutions corresponds to current in one direction or the opposite direction. But the wave functions are actually superpositions. So the eigenstates of this circuit are superpositions of persistent current states. That's why this is called the persistent current qubit. And then because we have a tunnel barrier here, but this is a quantum system, there is quantum tunneling through these wells. And that's how this superposition comes about. And the size of this barrier depends on the size of this small junction, which we usually call alpha. So here, controlling the relative size of these junctions is very, very critical. And in fact, this system is exponentially sensitive in these parameters. And that's the reason why people are a bit more afraid of using these devices. But nevertheless, they work very well. This is what the spectrum of energy levels looks like near this symmetry point. You see that the lowest 2 states, they approach each other. So this slope here, this corresponds to the current in one direction and current in the opposite direction. If this was a classical system, they would just cross. But because we have this quantum tunneling in the potential, then we get this gap. And at this point, that's where I have my 2-level system, because I have 2 states very, very far from the next level. So this is actually a much better 2-level system than the transmon qubit, the one I presented before. And moreover, the sensitivity to magnetic flux is suppressed to first order. You see the slope of this curve gives you the sensitivity of the circuit. So at this point, the sensitivity is 0. That means I'm insensitive to flux noise to first order. And that's where normally people operate these flux qubits for quantum computation. However, I wanted to highlight that this circuit has also been proposed as a magnetometer. And that's when you operate it outside of this sweet spot, where the slope is large. And if you want more details, you can find them in this reference. But essentially, this device is even more sensitive to the squid than the squid. Has even more sensitivity. But it's more difficult to operate. In reality, this is what one device looks like. You can identify very nicely this hyperbolic spectrum. This is the spectrum of a flux qubit. This is 0, but it's reference to half a flux quantum. That's also typical jargon of the field. At this symmetry point is where we get this nice Lorentzian line shape, and that determines the coherent properties of the qubit. Okay, so now you know 2 of these qubits.
This is the transmission coefficient. What are the measures?
Yeah, okay. I didn't talk at all about how to measure these qubits. This is a qubit connected to a waveguide. And in that case, you measure scattering through the qubit. So this is essentially transmission through the qubit. These measurements are actually not suitable for quantum computation because a waveguide is essentially like a loss bath. So normally you wouldn't want to use this qubit for quantum information. But nevertheless, it's a very nice tool to measure qubits, actually. But I'll talk about measurements tomorrow, how to measure qubits. All right, so we might make it to the end. Now I will start to talk about what do you do with these qubits. Now, you know 2 qubits. These are I would say, 99.9% of the qubits used in the world. So let's go and control these qubits. How do we do that? We have a 2-level system, right? In order to control the state of any quantum system, we need to supply external energy that is with photons that have a certain frequency, and we want this frequency to be as close as possible to the transition of the system. There is an actual analytical expression how to describe this scenario, which is using the Hamiltonian of a 2-level system. So for those of you not familiar with the way this is described, now this Hamiltonian I was using before has been truncated to the lowest two levels. So I only care about the lowest 2. The rest I forget because they are so far away that I don't need them. And if they're close by, there are techniques to make them invisible. So let's only assume we have a 2-level system. This sigma z is the Pauli operator. It's a matrix. It has 1 and -1 in its diagonal and 0 in its off-diagonal. And the eigenvalues of this matrix are +1 and -1. So these are the 2 energy levels. So that's this 1/2 here is to take into account that I have 1 and -1 in the diagonal, so the difference between 1 and -1 is 2, and divided by 2 I get the qubit energy. So this term just describes a 2-level system with energy omega q. Now I come in with an external field. And here, normally, there's an approximation that is implemented. I'm assuming that my external field is a classical wave, is a classical electric field or magnetic field, which has some amplitude and then some oscillation. And this field will couple to my 2-level system. So this term here is actually a dipole coupling. My qubit has a dipole which is pointing in sigma x, which is transverse to sigma z. And this is like the electric field. So this is electric field times dipole. This is like dipole energy. This Hamiltonian also describes spin 1/2 in a magnetic field. So this is what people developed in the 50s and 60s in nuclear magnetic resonance, where in that case you have the spin of a molecule or of an atom, and then you first apply a strong magnetic field in the z direction, and that splits the 2 spin states. So this is the Zeeman energy. And then people normally add a transverse field which oscillates. And with this transverse field, they are able to control the position of this arrow. So this is what is done in nuclear magnetic resonance. That means everything that was developed 50 or 60 years ago or 70 years ago is perfectly applicable to superconducting circuits, and in fact any qubit in general. So the language is for qubits is this sphere, is the Bloch sphere. This sphere has these three axes, x, y, and z. Normally we have our z being our axis where the qubit points. 0 is the ground state, and 1 is the excited state. And then anything that sits on the surface of the sphere is going to be a state of a possible state of this qubit. In the x-axis, it will be this kind of a state, this superposition, and the y-axis, it will be this kind of superposition. But in general, the state will look like this. So some phase theta, this one, and another phase phi, so azimuthal phase. And then in the lap frame, the system will be precessing. So this is simply what you get when if you have a spin and you put it in a magnetic field and then you tilt it, then the spin just precesses at the Larmor frequency. So this is the Larmor frequency of the spin. So in fact, this already gives us a way to control the Z. So this is like a Z rotation. Simply letting the system lay on any position and then just wait, and the spin precesses at the Larmor frequency. This is like natural precession of any spin. To control the theta, for that we need to apply this external energy. We need to drive the system. So what comes out of this Hamiltonian, if you solve the equations of motion of the state vector, you find that the probability to go from the 0 to the 1 state follows this formula. This is called the Rabi formula. And it depends on this parameter, which is the Rabi frequency. And in fact, this is nothing but the dipole energy of the system. And then this delta, which is the detuning. So when we are on resonance, exactly on resonance, this delta is 0, so it goes to 1. And then our frequency is simply the Rabi frequency, the bare Rabi frequency. That's what you see here, this blue trace. And this is the condition that allows us to completely transition from the 0 to the 1 state, from 0 to the 1. If we are a bit of resonant, then it's like we are driving with our driving field is not perfectly orthogonal to our spin, and it has some angle. So then the spin starts to precess faster, but its projection on the z-axis is smaller. So that's why this amplitude is decreasing. But on resonance, this gives us XY control. So now we have a spin, or an artificial spin, that we can control completely its axis. And this is data from one of the experiments that I participated in the past. This is function of time. And this is, in this case, this is some quadrature. I will explain tomorrow this vertical axis, but it's some signature from the qubit that does precess on time. You can in fact appreciate here that it does decay, so there are some mechanisms that make these oscillations to die out. But with good qubits, you can obtain decay rates of about tens of microseconds. So I think I don't have that plot here, but in the early days, the first qubits, their energy, once you would store an excitation in a qubit, it would last a few nanoseconds. All right. So, should I leave?
Maybe 5 minutes more. And
okay. I can continue tomorrow with the rest. So, with all the progress that has happened in the field, from a few nanoseconds now, it's not very difficult to get qubits in the tens of microseconds or even 100 or even a millisecond. There's some qubits that have managed a millisecond. So that's one of the reasons that people got so interested in this field, that despite being a solid state in an environment which is quite dirty and noisy, people managed to isolate these degrees of freedom and controlling them very, very well, to the point that it is conceivable to build a large quantum device. What I'm showing here, this is a T1 measurement. This consists of exciting the qubit with a pi pulse, and it's pi because we rotate the state by 180 degrees, and then we wait before we read out the state. So as a function of this wait time, the population of this qubit will slowly decay, and on average, it will follow an exponential decay. This is this T1 time scale of the qubit. But there is another time scale of interest, which is the T2, and that's the decoherence. That is, when we put the qubit in a superposition, so there is a phase between the 0 and 1, how long does this phase survive? And to do that, we first apply a pi/2 pulse. So that puts our qubit in the equatorial plane. And then we wait. This state precesses, and after some time, we apply another pulse, and then we project it in the z-axis. Our measurement axis is the z-axis. And as a function of time, we observe oscillations, and this is called the Ramsey oscillations. And you see that T2, this is for the same device from this paper, T2 is significantly shorter than T1. That means there are mechanisms which are not resonant with the qubit. They are actually low frequency noise that suppresses this phase. There are some tricks you can play. For example, this is the spin echo. If you apply a pi pulse in between these two pi/2 pulses, this pi pulse inverts the effect of the noise, at least the low frequency noise, and it gets cancelled out. So you see by one pi pulse, you can almost double the duration of these oscillations. You can apply more complex techniques to it's called a dynamical decoupling, to essentially suppress this low frequency noise. But T1 is the energy of the qubit. There's nothing you can do about T1 except adding more energy and with feedback and then correcting the state. This is a bit what the setup looks like for one qubit experiment. We have, with this XY control, we have a vector generator, local oscillator, and then they are mixed, and this signal is sent down through some attenuators to suppress electronic noise, and this, with some filters, goes into our device. The Z control is simply applying some DC pulse to modify the qubit splitting and control in this way the Larmor frequency, and this goes also straight into the device with some filtering. And finally, we also normally need a DC source, like a low frequency source that has usually filtered by copper powder filters and added to the DC, to the Z control, and then into the device. Also, normally we have a coil that biases the entire chip if that's required. And this is the output chain that I will talk about it tomorrow. I don't want to say anything now. This is our lab in Barcelona. So this is the setup we have for our single qubit. This is this AWG. This is a network analyzer. Here we have the micro resources there. Inside of the fridge, this part, these are our few coaxial cables. This is actually quite simple experiment. If you look at, if you want to see what the big experiment is, you can look up the Google team, their papers. They have a few tens of these cables. So it's moving, the whole field is moving into this direction. Large fridges, many cables, many qubits. And finally, in this experiment, in the bottom part, this is the mixing chamber plate. We have a box here and another box there. This is an aluminum box. This is a copper box. These are cavities for this experiment. We use them to isolate our qubit. I'll talk about cavities tomorrow. But essentially here we have two independent experiments in this setup. Okay, so I come to the sources of noise, and I think that may be a good time to stop. And then tomorrow I will take it from here, because I think I would like to spend some time discussing this part. So thank you for your attention.